Then we have the last talk now before the lunch break by Patrick Morris on Roman's potential impact on the census of a wolf massive star in transition.
Okay, yeah. Let's see. Okay. Okay, does that come in? Can you see my title slide? Yeah.
Yes.
Yeah, great. Okay, so I have to apologize here. I can't turn my camera on, as Jennifer said. The tech gremlins are out today, so I'm going to just leave you with some beautiful scenery there of the nighttime at Joshua Tree, and just press on here with my talk on Roman's potential impact on the census of evolved massive stars in transition. And what I mean by transition is this group of blue stars, the blue supergiants, luminous blue variables, and Wolf-Rayet stars, which, as Jennifer and others have sort of set the stage for already in previous talks, that these are coming off the main sequence, and their lifetimes before going into supernova of different flavors is actually fairly brief. And so while I think the roles of massive stars as supernova progenitors and long gamma ray bursts and mergers and so far have been pretty well covered in these previous talks, what I want to do is concentrate more on a problem that's been known for a number of years now, and that's in the population statistics of these stars. So basically what my talk is about is focused on finding these stars, and the main point being that the model predictions do depend on population statistics given the number of different ingredients that have to go into those models. And so knowing how the population numbers compare, I think is actually really critical. And so far we've only come up with around 10% of the total number of predicted galactic Wolf-Rayet stars and LBVs. And so the question is whether the census is incomplete due to obscuration by dust, which is the most common explanation, aside from possibly the models being wrong, which is always possible as well. And therefore, there's still a lot to be answered about the Wolf-Rayet to O star and Wolf-Rayet to red supergiant ratios, which are important for constraining post-main sequence lifetimes and their formation environments and so on through their distribution in the galactic plane. As well, okay, so if you've never seen, I haven't seen any Wolf-Rayet spectra shown yet, so I thought this would be a great place to show one here. Obviously, it always fails. Actually, hardly ever fails to impress, mainly because of the strong emission line spectra that these stars have, and this is mainly lines of helium, carbon, nitrogen, and some oxygen, depending on spectral type. But there's also this excess that starts here. Can you see my cursor, by the way? No.
Yes, we can see.
Okay, good. Yeah. So starting around 1 micron here, then you start to see this free excess relative to an O supergiant spectrum in black here, and that's because of the strong free emission that you get from the scattering of hydrogen atoms in the neighborhood of helium ions. And so we can take advantage of these spectral properties to see whether this can help us in searching for additional stars of this type. So if we assume that the population shortage is mainly a reddening problem in the observable sky, then we should have some luck as we go to the IR, excuse me, where the obscuration goes down, and we can exploit this unique shape of the SEDs. And so these properties, these continuum line properties, do actually drive the colors of these stars almost uniquely from other populations. Using a broadband approach that we developed here at IPAC, led by Skylar Van Dyke and myself, along with some students and postdocs over the years, and then starting with the 2MASS and then Spitzer colors to select candidates, and then following those up in the near infrared, we immediately increased the census of Wolf-Rayet stars by about 30%. And this was a big jump and gave us a lot of confidence that we're heading in the right direction. But of course, I mean, there's a lot of variability in the success rates of finding these stars when you have to follow them up at the telescope in such a scheme like this, and it's there's a lot of biases involved in avoiding crowded regions and limiting yourself to a certain range of K-band magnitudes to avoid spending too much time excuse me, at the telescope. So the other observation, more expensive approach uses narrowband filters on key emission lines, but the success rates are about the same, but it just takes a lot longer at the telescope. So an important point is that the near infrared colors are not alone going to get you a good selection of candidates that's manageable at the telescope. They do segregate from the rest of the population, but there's still really just way too much overlap with the other populations. And so adding in Spitzer magnitudes and colors does help a lot, but then we start to get into overlaps with other populations of red objects like the YSOs and AGVs and so on. But even with a measurable increase in the census, let's say over the last 15 years or so, we're still left with this picture of the distribution of these stars, which is in tension with where they should be, which is in clusters and associations. And this is evident in the left plot here. We produced about 10 or 11 years ago, where the cluster is identified by the upside down triangles. Hope you can see those are indicate where the Wolf-Rayet stars that we detected to that point, which was about 325 stars. But what you can see is the vast majority of these stars are scattered in the spiral arms outside of those clusters. So in the age of Gaia, things have improved just a little bit in terms of where these stars are located, where they're expected to be located. But I think what Gaia really helped us out was just basically better defining what is a cluster association, and that allowed us to probe deeper or associate the known stars with those clusters and so on, and so that you can see this tension is reduced a bit, but that most of the Wolf-Rayet stars are still isolated. And so this is contrary to how massive stars are likely to be formed. It's the theory of massive stars, and this represents a significant tension. So what Roman offers us then is HST-like angular resolution and a set of new color attributes for finding the evolved stars. And with the filter coverage that I'm showing here, we get coverage of the optical continuum, formed mainly by electron scattering in the wind, to the free excess regime, and then attenuated by the strong emission lines, some of them being really valuable classification lines. So we get this, what we can do with this then is construct SCDs. We can use the SCDs from all these various classes of stars to construct color and color magnitude diagrams, set our selection criteria. And I'll just note that the reddest and bluest filters give us a really decent estimate of the stellar temperatures, although this becomes a little bit more uncertain for the Wolf-Rayet types because they break further from hydrostatic equilibrium. And this is one of the reasons that the MK classification system doesn't work so well for these stars, because there's no applicable color temperature calibration without taking into account the wind densities. Okay, so then if we then include a prism or GRISM survey, we get the spectral types, and we can carry out a quantitative analysis with basic line measurements using, say, equivalent widths, and then fit these to stellar wind model predictions that then give us the bulk stellar and wind parameters. And this is an example of what that looks like. Just using equivalent widths of several lines cast as contours of temperature on the x-axis here, and radius on the y-axis, or a so-called transform radius that contains invariance, including the mass loss rates. And then using a few approximations on the wind speeds and luminosities based on spectral type, this is still reasonably okay. As a first approximation, one can get the mass loss rates. And then very importantly, this wind parameter, this wind performance parameter, eta, defined as a ratio of mechanical to radiative momentum. And this is one of the measures of how efficient a photon-driven wind converts its energy into pushing out mass. And it turns out that this number is very high for Wolf-Rayet stars and LBVs. It's usually around 10 or so. And in fact, this can actually be used as a selection criterion on LBV candidates. Okay, but this doesn't actually address the LBVs very well. All we're doing here is just finding those stars, including the blue supergiants that may be LBVs. It was obvious from, as Jennifer mentioned, that just having a spectrum is one way to identify a candidate, but that's just a static snapshot. But let me say first that true LBVs are very easy to identify because of their eruptive nature. This was stressed also in the previous talk. So any transient survey at optical wavelengths is going to pick them up. And if the erupting star isn't destroyed, then monitoring their light curves and spectra, that will help determine whether it's a supernova or a supernova imposter. And like the Wolf-Rayet stars, we should have many more of them than are currently known. There should be at least 100 or so more in the galactic plane, in the Milky Way, and we only know of about 15 bona fide cases. And of course, this leaves open the same questions by this deficit. But we do think there's a way to narrow down the set of blue supergiant stars that look like LBVs to be most likely in some phase of activity to be like that of the LBV. So we want to turn LBV candidates more from just a snapshot candidacy into something that resembles LBVs at the level of their variability before they erupt, either before or after, for that matter. And this is to characterize looking for characteristic signal microvariability that's been shown in test observations of a small number of known and suspected LBVs in the LMC. So these are what candidate LBVs look like based on their appearance as emission line BE stars. When in quiescence, cases like P Cygni and AG car look almost exactly like all of these stars that I'm showing here in the H and K band. By the way, these make great wavelength calibrators in case that ever is a need for the GRISM. But okay, because of the similarities in colors between these stars and the Wolf-Rayet stars, we get a kind of a database of candidates almost automatically when searching for Wolf-Rayet stars. So even a first visit back with Roman or with Rubin to some of these, to some of these stars. I mean, this will leverage how well we think this method might work in finding LBV candidate stars to a level that indicates changes in effective temperatures, at least up to the point that that they would have made themselves already obvious in other transient surveys. So another way to actually look at this in terms of microvariability diagnostics comes from certain lines that are very responsive to changes deep in the wind of a hot star. And I mean, especially those lines whose upper levels are populated by connecting transitions in the UV. Brought this up a couple of days ago in Eric Schau's talk. And one of the best examples for that is the 1.08 micron line shown in the Gaussian diagram here. So whenever the field attenuates, the line responds. And the best example of that has been in LBVs like Eta Car and other extreme stars. So on the other hand, when the variability is driven by pulsations, then we should see line strength variations on the order of days given by the dynamical or free fall timescales. And of course, this can get complicated by circumstellar material in the line of sight. This basically adds noise to the periodograms. Okay, then there's H alpha, which fortunately is accessible with a prism and shows very strong sensitivity to the Lyman continuum. So any changes in Lyman photon fluences will be observed as changes in the profile shape and emission strength, as I'm showing in theoretical calculations here in the upper left. H-alpha is also a favorite for monitoring variability, as I've shown here on the right in the supergiant BE star, which I think is a target for Rubin and pointed observations, which is regarded also as a sibling to Eta Carina because of its very high wind performance and shows enormous changes in profile shape and strength on the timescales of a few weeks, maybe even shorter. And the important thing here is that such lines are resolved very well, except for the narrow P Cygni component you see, on the left side of the profile, but it also resolves these electron scattering wings, these broad scattering wings, red shifted and blue shifted, which are important diagnostics for clumping in the stellar winds. Okay, so I'm basically out of time, so let me just summarize here then that an imaging survey plus GRISM will reveal evolved massive stars with almost immediate impact on their population completeness estimates and distributions, spectral types, stellar wind parameters, and these statistics, especially in the ratio with O and red supergiants and with the nitrogen and carbon-rich categories of Wolf-Rayet stars are very important to test the stellar models and lifetime predictions. Specific helium and hydrogen lines are very sensitive to UV field variations, and so I think we can use this as a means to detect LBV activity up to the point, let's say LBV activity of the kind that that known LBVs exhibit when they're in quiescence, and this narrows the LBV lookalike candidates to actual candidates. And then finally, yeah, there's a great synergy coming with Rubin, and at least possibly you could lay it in a second half of the mission for variable stars and multi-epoch photometry. And I may not be it looks like I may be the first person to say this, but it's regrettable that we don't, with spectroscopy, can't have the helium-1 2.058 micron and the row vibrational H2 2.112 lines. These are really great diagnostics in hot star winds as well, especially for revealing molecular material that you may not otherwise know about just by observing in the near infrared with broadband colors. And I think that's it. Yep.
Okay, thanks a lot, Pat. There are no questions, and it's also time for the break, but I just want to ask one question before, because it was a lot of information in a very short time. I just want to clarify one point. You are saying that you can distinguish based on photometric microvariability LBVs from other blue supergiants, for example?
No, not necessarily. No, from the blue supergiants, when they're microvarying, I think all that really does is establish them as being in a state which normal blue supergiants don't exhibit. So I think this was done carefully with test observations of the both an LBV candidate and an LBV, a known LBV in the LMC. And they had variability at about the same level, but the blue supergiant, which was a candidate, was also a star which had a very high wind performance. So it does also. So I think you need to select these stars also based on the wind density and their mass loss rates, and that we can get.
Okay, thanks a lot.